Howdy, this is another episode of Dinosaur Parkour. I'm your host, Chris P. Fried. Today's topic is IMS, Get Next Root, Reading Roots in a Batch Program. Get Next Root is used to process all of the roots in a database. Therefore, it is generally used in batch programs. Since the norm is to process all the roots in a database, the programs tend to be long running. It is rare to use Get Next Root in a transactional program, which is also known as an online program. To be clear, what we are talking about is Get Next Root, not Get Next Root using a secondary index, not Get Next Root plus reading a child. This slide shows a pseudo call of the GetNet customer root into an I/O area. It also shows the actual native call. This is known as a native or call level. A call is made to CBL to DLI or COBOL to DLI, which is an application interface or a black box which does the actual communication with IMS. 4 parameters are being passed to this call. Parameter number 1 is the IMS function to be performed, in this case, GetNet. The function is a 4-byte alphanumeric field. It is defined here as IFC-GN or IMS function code GetNet. The value is GHN, which stands for Get Whole Net. I'm only going to mention the whole versions of the calls, and there's very little advantage to the non-whole versions of the Get calls in most programs. I suspect that will be a controversial statement, but IBM's IMS documentation makes similar claims, and XactDLI only uses the whole version of the call, which will be mentioned later. The second parameter is the PCB Mask. PCB stands for Program Communication Block. This is how IMS and your program communicate with each other. IMS places a status code for each IMS call in a field within this block. It's explained later how to map or get access to the PCB. The third parameter is the I/O area for the data being returned by IMS. In this example, the customer root segment is being returned. The fourth parameter is the SSA, or the segment search argument. This tells IMS which segment to get. Which IMS static code should be handled by the program after issuing a Get Next root call. Spaces, which means the call was successful, a root segment was found, and the data was placed in the I/O area. GB, the end of the database was reached, no data is returned, so whatever is in the I/O area from a prior call is still in that area. If the call was made against a FastPath database, or what's known as a data entry database, FW might be returned. This means the call was successful, however overflow buffers might have been used. The FW is a FastPath specific static code and should be treated like basic. Now, if the call is successful, parentage is on the root and position is on the root. The position and parentage are very important if a Get Next within parent call are done later. Get GNP or Get Next within parent calls are covered in another Dinosaur Parkour session. It is my personal preference to isolate the Get Next call and the evaluation of the static code in a COBOL paragraph. In other words, issue the Get Next call, check the static code within the PCB. A suggested naming convention is implied in the evaluate, such as PCB static code dash and the database name. Try to keep the processing of the data to a minimum. In this example, the checkpoint read count is incremented by 1, but there's nothing from the data that is processed in this paragraph. Okay, how does one know the name of the segment? Well, let's take a look at the PSB, Program Specification Block. This is your program's view of the IMS database. There might be 30 databases in the shop, but your program only needs access to 2 of them. In this example, the customer database and the savings account database, which are shown as two PCBs or program communication blocks. For PCB number 2, there might be 8 segments in the customer database, but your program only needs access to 4 of them, the root and 3 of the kids. The proc op on the PCB level gives read and update access. Proc op GRP means processing option get, replace, and the P means allow path call for all of the segments. P only means this for full function databases. P means unit of work processing or UOW processing for fast path databases. PCB number 3 has a proc op of GP on the PCB level. However, each segment is coded with a proc op which mostly overrides the one on the PCB. There are certain options that apply to the PCB, and those are not overridden. In this example, save kid 1, it allows get, insert, replace, and delete, which overrides the GP that was coded at the PCB level. Now, save kid 2 does not have a proc op coded at the send level, so it uses the proc op that's coded on the PCB level, which is GP. Save kid 2 can be read but not updated. There are 2 PCBs coded in this PSB. They are numbered PCB 2 and 3. So where is PCB number 1? Well, PCB number 1 was created by IMS. This is a PSB for a batch program. Batch programs have to take checkpoints in order to commit the database changes. IMS needs a PCB. IMS needs a communication block for taking checkpoints. So IMS creates what's known as an IO PCB, and that will be PCB number 1. So therefore, the first PCB that is coded in the PSB source becomes PCB number 2. Hopefully the DBAs in your shop add comments like the one shown in this example to reduce the confusion. This slide shows the same paragraph that was shown earlier. It had been updated to follow the naming suggestion. The paragraph name is updated with the database name. The root seg has been replaced with custroot, which is the name of the root segment in the customer information database. The I/O area contains the name of the segment. And notice the IMS call and the evaluator is isolated in this paragraph with a minimum processing logic. I will explain later why this is done. But first, let's look at some bad code. This is something I've seen too much of. This logic has been coded in a linear fashion. The I/O is coded in the main processing logic. The get next is not isolated in a paragraph. So basically the programmer went, I need to process all of the root. To do that, 1, I need a loop, code to perform until. Number 2, get the root. Number 3, evaluate the status code. Number 4, process the root. Number 5, code the end perform to end the loop. 6, do whatever cleanup stuff is needed after the program is done. Okay. There's a problem with this logic. Let's pretend there are 2 roots in the database. So enter the loop. Get next custom root, which gets root number 1. Status code of spaces, add 1 to the checkpoint counter, process root number 1. Loop again. Get next custom root, gets root number 2. Status code is good, process root 2. Loop again. Get next custom root. There's not another root in the database. End of database is reached. IMS returns the status code of GB and does not put any data in the I/O area. Evaluate the status code, which is GB, set the end of database flag to true, process what? IMS did not return any data to the IMS IO area. So the data for route 2 is processed again. Exit the loop because the flag. So the programmer might go, this can be corrected by adding an if statement. Well, one, this if statement is ugly. It also wasted a bit of CPU because the if statement is only important when the end of the database is reached. The process, the root logic, had to be indented, which makes it harder to understand this logic. And it makes the code ugly. So the programmer at this point might go, okay, the getNet can be isolated in a paragraph, and they do that. So yeah, the code looks better. The main loop is much cleaner looking. There's a beginning of the loop, getNet's cuss root, you process the root, and you loop again. The only problem is this code is still wrong. The last root is processed twice. Adding the if end of database is not the answer. And yes, we've covered this already before, but before the IMS calls themselves were embedded directly into the main logic, the main loop logic. Just isolating the IMS calls into a paragraph by themselves doesn't always solve the issue. There's some other restructuring that needs to occur to the loop. It surprises me how often I see this gotta handle the GB or the GE workaround, meaning the silly if statement. And by the way, the GE means the segment was not found. This is the pattern to be used. This pattern is known as prime to pump pattern or priming to read pattern. I like calling it prime to pump. Here's why. Have you ever used the technique of sucking fuel from a car into a gas can? One end of a hose goes into the tank of the car and the other end is placed in the can. Well, nothing happened. What you got to do is you've got to suck on the hose until some fuel starts to come out of the car, and hopefully just in time you push the hose back into the gas can before you get a mouthful of fuel. That first getNet cuss root coded before the perform loop is priming the pump. That's the prime and read. Get the first root, enter the loop, process the first root, see if there's another root at the bottom of the loop. If so, process it, repeat the loop, and keep repeating the loop until that getNet at the bottom of the loop gets to GB, which means no more roots are found. That means the database is empty and you exit the loop. Now, if the database is empty to start with, in other words, there's no data in the database when the program starts, the prime and read loop will get a GB and never enter the loop. What about GE? Well, it's not going to be returned. This is a getNet root. A secondary index is not involved. The call either finds a root or it reaches the end of the database. If it makes you feel better, the GE can be included in the evaluator as shown here. There's an implied OR between the when GB and the when GE. In other words, when GB or when GE set the end of database condition to true. This slide shows the prime and read logic along with the checkpoint logic. Now, some of the overall logic is missing, specifically the initial checkpoint and restart portion and the actual checkpoint call itself. This is a plain getNet root call, fastpath HSSP, high-speed sequential processing, or the unit of work processing is not involved in this. When a checkpoint call is issued, IMS loses the current position. So let's assume that the checkpoint is invoked every 500 root. The program will process 500 root, and then the checkpoint call is made. During the checkpoint, IMS destroys the current position, and so now the default position is at the beginning of the database. So if you just simply reissue the get net root call, you're going to get the first root in the database, and then another get net call would be the second, and you just will keep doing that until you reach root 500 again. It's time to take a checkpoint, lose position. Now you're back to processing the first root in the database, the second root in the database, till you hit 500, and you're just in this infinite loop where you're doing I/O, but you're not making any real progress. You just keep processing the first 500 roots over and over. And this will continue until somebody notices and cancels the job. The solution to this problem is to use a get unique to reposition back to the current root at time of checkpoint. So you take the checkpoint, and a part of the checkpoint logic, you're going to save away the key, which is the key for root 500. IMS does the checkpoint, loses the position. Now you perform the get unique customer root, and this paragraph would issue a get unique call for the customer root and ask for customer root 500. This puts the position back on root 500 so that when you exit this paragraph and then do the get next root, it will move to root 501, and now processing continues normally. So we have resolved the problem. Yay. Let's take a quick look at that get unique paragraph again. Notice that it's handling when basis and when GE. Well, the reason for doing that is, what if this program was deleting root? Sometimes it deleted a root. Well, it is possible that root 500 was deleted at the time we took a checkpoint. Remember, the checkpoint is committing the data, so IMS is committed to delete. So when I issue the get unique call, root 500 is no longer in the database. So in that case, a GE was returned. That's not a problem, because IMS is going to be positioned where root 500 would have been in the database. All I have to do is make the code handle the GE in this circumstance. Now, most programs are not deleting root, so they don't have to worry about this GE logic. They just reposition on basis. They just do that get unique, and when basis, they continue. But I wanted to explain why this GE was coded in this example. This slide shows 5 roots spread across 3 CIs, or vSAM control interval. I've only worked with IMS over vSAM. I've never worked with IMS over OSAM. The dotted blue squares represent CIs with data. This picture represents either an HDAM or a FastPath data entry database, or DEDB. Thus, the root segments are spread across the database using a randomizer. IBM's default randomizer just simply tries to spread the data evenly in an even bell curve across the database for any key. So the data keys will appear random because it is a hashing routine that's involved in that. The purple star on the far left is the current position in the database. It's not on any segment because the program has not issued any IMS calls. With the HDAM databases and the DEDB database, or data entry databases, the first call is going to get the first get next call is going to get the first root in the database. I can't speak for other types of databases how they work, but that is how the databases I've worked with will behave. The program starts. It does the priming get next root call. IMS starts scanning the database from the beginning. There might be 10 empty CIs at the beginning of this database before the first root is found. So IMS will look at those 10 CIs until it finds a wrap in CI11 that says CI11 contains a root. The wrap, or the root anchor point, points to the first root in the CI. So IMS gets the first root, which is a root with a key of 1005. IMS returns the data to the I/O area in the program. Parent is on route 1005 and position is on route 1005. The program then processes route 1005 and it's not time to take a checkpoint. Now things get a little more interesting. The program issues a call to get another route. Now there are two routes in wrap/CI11. Route 1005 has a twin forward pointer that points to the next route in this route anchor point. IMS follows this pointer to get the route with a key of 3127. IMS returns the data for this route. The status code is spaces. The parent is on the route with a key of 3127 and the position is on the same route. So we issue the get next route call again. There's no more routes in this CI. So IMS leaves route wrap 11 and scans until it finds another route anchor point that contains data. That might be CI or wrap number 12, or it might be CI 100. At some point, IMS finds a route anchor point that points to route 9963. Position and parent is put on route 9963 and the program processes it. Get next again. The twin forward pointer is null, so IMS stands looking for the next wrap that contains data, which is the third blue square where the wrap points to route 96. Get next again, and IMS goes at route 555 using the twin forward pointer. This is the last route in the database. When the get next is issued again, IMS will scan until it reaches the last route addressable CI in the database. And so there are no more routes in the database, so IMS does not return any data to the program, but it does update the status code in the PCB, program communication block, with a status code of GB. Now, most documentation states that the position is unknown. However, for data entry databases and HDAM databases, if you issue a get next again, you'll get the first route in the database. Okay, let's take a look at the PSB again. Remember, the first PCB in the PSB is actually number 2, because IMS created a PCB for taking checkpoint. The I/O PCB is PCB number 1. Therefore, the customer info database becomes PCB number 2, and the savings account database becomes PCB number 3. This slide shows XZDLI, or command level. A quick note about XZDLI. It's not owned by the IMS group at IBM. It is owned by the KITS group, or the CICS group. So XZDLI can be used in online KITS program or CICS program, and it can be used in batch program. Yes, it's also allowed in batch program. Now, the XZDLI get next. It's not GHN. XZDLI convert the get next within parent, and the get unique into whole call behind the scenes at execution time. Thus, all calls done with XZDLI, all get calls, are whole call, all of them. If a PCB has get only coded for the processing option, such as ParkOp equal GOT, the whole is ignored. Using PCB and an offset number. The using PCB is an offset to the PCB to issue the get next command again. The customer info database is PCB number 2. Remember, don't forget about the I/O PCB being number 1. You can hard code the actual number 2 as part of the using So you can say using PCB open paren, the number 2 close paren. But that's not recommended because in production programs it's not very much of a documentation. It's better to use a variable. In this example, the PCB, in this example, it's PCB dash cus dash info, which is more descriptive and it's defined as a binary half word. Thus, this field is defined as pic S or pic 9 open paren 4 close paren comp, and it has a value of 2. It's a binary half word with a value of 2 stored in it. The segment keyword simply names the desired segment, which is cus root. The N2, that's the I/O area. So at the N2, and then you provide it with the name of the I/O area. I like using I/O dash followed by the segment name. So in this example, it would be I/O dash cus root. And that's pretty much it for this get next call. At this point, it should be fairly clear that the pseudo call used in all the prior slides are just a stripped down version of the exact DLI. The native call, also known as call level interface. Call the black box, which is COBOL to DLI, using parameter 1 at the function. So parameter 1, which is the function, is a 4-byte or 4-character field that contains GHN for get, hold, next. Remember, that DLI auto-insert the H or the hold into all of the get calls. So I'm going to basically do the same thing. Now let's skip the second parameter until the next slide. The third parameter is the I/O area. Since this is not a path call, IMS only returned the customer info root segment. The I/O area was named IO-cus root. The fourth and last parameter is the SSA, or the segment search argument. This one is simple. This is what's known as an unqualified SSA, meaning it's not coded with a where condition. In other words, this segment search argument says, give me a cus root, I do not care what the key is. Since the IMS call is to get next, since the IMS call is to get next, that means that this call can be stated as, give me the next cus root after the current position. So if IMS is on the 10th root in the database, that means give me the next root, which would be making IMS go look for the 11th root in the database. So back to parameter 2, the PCB mask. The customer info database is PCB number 2. But it's not an offset number that we work with here. We actually got a map on top of it. In the code, most programs will use entry DLI to COBOL using. And that's what it appears when I do a Google search. It seems like most programs use entry DLI to COBOL using in order to map the PCB mask. But the last shop where I worked, the entry statement was not allowed by the audit group. So that shop was able to figure out how to get procedure division using to work. So that's what would be used instead. But the using part is the same. So the using part mapped the order the PCBs are passed by IMS, meaning IMS is going to pass the PCB areas in the order in which they're coded in the PSB. So the using statement has to match up with what's coded in the PSB, including anything IMS auto-generated. The linkage section does not have to be coded in the same order. In fact, the linkage section doesn't matter. In this example, the cus info PCB is listed third, and that's not a problem. But if you don't want to remember which one's important, just get everything lined up the same.